All right. So now we're ready to start back up. I'd like to introduce Dr. James Franklin, who we really owe doubly here. First, approximately for being willing to work quite late Australia time on our behalf in Europe and the US, for whom it is rather earlier. And secondly, and most importantly, for really being the kind of the dean of this whole enterprise and pulling together so many different resources on Aristotelian philosophy of mathematics, encouraging many other researchers, including myself, in the area. And so we really appreciate him for that pioneering work and for that kind of coordinating role. And his talk here, I think, is going to speak a little bit to that sense of the layout of the field. So take it away, James.
Thanks. Yes, well, I'll start with an overview of the Aristotelian realist option in the philosophy of mathematics. I'll explain what Aristotelian realism says and why I believe it. Then I'll say something about how it fits into the general field of philosophy of mathematics and how it contrasts with the standard options in the field, Platonism and nominalism. Finally, I'll give a quick overview of some of the players in the field to give some idea of the variety of what's on offer. There is quite a lot on offer. This is the Phil Papers category, Mathematical Aristotelianism. It contains 105 items, which, as you can see down the bottom, is just a touch ahead of fictionalism with 99 items. Of course, it's not as big as Platonism or nominalism. I'll give later some sense of what's in there. Well, the basic idea of Aristotelian realist philosophy of mathematics is that mathematics is a science like any other, or up to a point anyway. Biology is about living things. Sociology is about the social aspects of reality, chemistry, etc. And mathematics, likewise, is about certain aspects of the physical world or any other world that there may be. So what aspects are we talking about, and why should you believe that? Let's start with a thought experiment. What if language, thought, and symbols, and in fact mathematicians using them, were abolished, and abstract entities as well? Would there be anything left that you'd call of a mathematical nature? Here's the world of the dinosaurs, artist's impression. In that world, there are no symbols, there are no formal systems or people to have the formal systems. And if abstract entities still exist, maybe you can't really cancel them, well, they're not there, they're somewhere else. Now, just considering that purely physical and biological world, would you say that there are any properties of it that you'd call mathematical, using that word as loosely and widely as possible? I'll just take a pause while you think about it. Well, there are. What about symmetry? The dinosaurs have bilateral symmetry, approximately anyway, while the volcano and the palm tree bottom left, have an approximate circular symmetry. Think of looking down at them from above. The eggs too, quite symmetrical objects there. Well, symmetry is one of the basic objects of mathematics. There it is in the world of the dinosaurs. The flow of the river in the middle, is continuous, at least down to some tiny scale, while the animals and the tussocks of grass in the front are organized discretely. The discrete versus continuous contrast is one of the basic organizing themes of mathematics. Ratio is there too. You can imagine, if you imagine this, if you kind of animate this thing in your mind, you imagine the big dinosaurs lumbering around slowly, and the small one down near the eggs is jumping about in a sprightly way. The reason for that is that mass scales as the cube of length, while muscle strength scales as the square of length of the cross-sectional area of the muscle. So large animals have less muscle strength for their mass. Ratios are in the physical world, and facts about them have that kind of physical consequences. So just to list a few of the mathematical properties of the physical world: symmetry, continuity or discreteness, ratio, order, relationships of scale. That's not to say that symmetry is possessed only by physical objects. For example, arguments can be symmetrical if their bottom half repeats the top half in the opposite order. So we find in the physical world such properties as symmetry, continuity and discreteness, ratio, order, relationships of scale. Well, in that case, there must be a science that studies the truths about those properties. You think about what it is, well, it's uncannily like mathematics. For example, if you want to classify the different kinds of symmetry, you get group theory, which is the central part of modern abstract algebra. And furthermore, those properties are directly perceptible. Actually, the perceptual system is set up to be very sensitive to them. Sorry. For example, this classic diagram shows how easily we perceive the ratio of height to width. Well, it's literally perception that you see, tall and thin versus squat and stubby. There's a saying that if your face is asymmetrical, you'd be well advised not to go into politics because it shows up badly on television. Now, if you've read any standard philosophy of mathematics, you'll have found the introduction I gave to be very strange. I haven't talked about the usual things like formal logic and set theory and abstract objects or symbols. The field is dominated by two main alternatives, Platonism and nominalism. They avoid mentioning anything about mathematical properties of the physical world. So let me explain next how Aristotelian realism fits into the big picture of options in the philosophy of mathematics and how it contrasts with Platonism and nominalism. Here's a basic division diagram of classifications of philosophies of mathematics. Philosophy of mathematics is divided into realist and nominalist. Realist says mathematics is about something, it has a definite subject matter, and nominalism says it isn't about anything. Nominalism comes in several flavors. A view popular among scientists is that mathematics is just a language of science. Logicism, in Russell's version anyway, said that it was just how to make inferences. Formalism said it was the manipulation of uninterpreted symbols. And I won't go into those further. Fictionalism is another form. It says nominalism is true, but sometimes it's convenient to pretend it isn't. Realism comes in two kinds, Platonist and Aristotelian. Platonist realism says that mathematics is about a realm of classical abstract objects, such as numbers and sets, which are eternal, non-physical, acausal, imperceptible, and independent of thought. Aristotelian realism, as just explained, says that the object of mathematics are properties that are realizable in the physical world. They're causal and perceptible. And I say realizable rather than realized because a realizable property is not guaranteed to be actually realized. That's for the world to say. For example, if at a time just after the Big Bang, there were only 5 things in the world, then 6 wasn't realized. But it's the sort of property that could be realized. Now, one clarification I need before we go on. Aristotelian realism is not empiricism. although Aristotelian realism says that mathematics is in one way a science like any other, that is the science of properties of the world in applying to the physical world, in another important way, it isn't. And that's because it's about necessities. Here's a standard example, which also clarifies further the sort of properties that are the subject matter of mathematics. It's Euler's example of the bridges of Königsberg in the 18th century. They're pictured here. 4 land areas, A, D are islands and B, C are the banks of the river. And it's connected by 7 bridges. They're a little hard to see there, so let me move to the next slide where it's a lot clearer. Banks of the river, top and bottom, islands in the middle. And there's 7 bridges, the hard bars, black bars. But the structure is the same. Now, the citizens of Königsberg found that it was apparently impossible to walk over all of them just once. That is, without walking over one of them twice. Now, let's just pause a moment while you either remember the thing or try it for yourself. See if you can walk around in your mind's eye all 7 bridges without having to go over one of them twice. Well, you won't get far because it's impossible. It's a provable mathematical necessity, and Euler proved it. But notice carefully, it's about the actual arrangement of real bridges. It's not about some abstract model of them or some Platonic entity. Euler's proof was about walking over real bridges. It says the impossibility is about that. Of course, you could make the bridges or the citizens different, but with the bridges and walking being actually what it is, it's a provable mathematical necessity that the actual citizens can't walk over the actual bridges once and once only. Platonism and nominalism both find that unintelligible. Okay, that's the introduction to what Aristotelian realism is trying to say. Now let's go back to the mass of things that have been written about the mathematical Aristotelianism as surveyed in the 105 papers in Phil Papers. And I'll spend the rest of my time quickly surveying a few of the items. Of course, just my favourite ones, I suppose. Sorry to those left out, 105 is a lot. Well, there are 3 kinds of works in there. There's works about Aristotle's own philosophy of mathematics. There's ones on modern Aristotelianism, and which I've been concentrating on so far, and there's Thomist ones. Well, okay, about the Aristotle's philosophy. Aristotle did not write a whole work about mathematics, but he understood well the mathematics of his day, and his various remarks on both mathematical entities and proofs give a more or less coherent position, which has, of course, been studied intensively. Bostock's overview in the Oxford Handbook of Aristotle is a good place to start. I find interesting the 2 pair of articles by Emily Katz and Andrew Irvine addressing Frege's very influential argument as to why mathematics can't be about the world. His overlooking the Aristotelian option is where his argument went wrong. There's an interesting aspect of Aristotle's work is its relation to Euclid. It's a rather fraught matter because Euclid's Elements avoids mentioning philosophy, but it implements Aristotle's model of a science quite well, organized from self-evident axioms, and also a philosophy of number is extractable from it, if you like to put in the effort. Hossack's book mentioned there takes off from that idea. It's rather surprising that it has plenty of references in it, but the last person that he refers to favorably is Euclid. There's also work on the special topic of infinity in Aristotle, as in the previous two talks. I wouldn't say that that's a topic of special interest from the point of Aristotelian realism overall, but though it's certainly an interesting special topic in itself. I must say I wish the people working on Aristotle would spend more time connecting to contemporary questions. Look, if Aristotle got it basically right, it should still be right in principle, but it might need some adaptation to 2,000 years of developments in mathematics since then. The second division of contemporary work on Aristotelian realist philosophy of mathematics is, here are some of the authors that I'll mention briefly. Plenty of these, especially in the last, 10 years or so. Allow me to mention my own book, An Aristotelian Realist Philosophy of Mathematics. Mathematics is the science of quantity and number, which gives a complete story. It says exactly what properties of the world are the subject of mathematics, namely quantitative ones like ratio and structural ones like symmetry. It deals also with epistemology, answers objections, and so on. The cover image is the rose window of Strasbourg Cathedral, a spectacular example of symmetry and also of its immediate impact on the senses. Here are some other works I think are interesting, among many others. The two by Donald Gillies, An Aristotelian Approach to Mathematical Ontology, and the late Dale Jacquet's one toward neo-Aristotelian inherence philosophy of mathematical entities. These are overview, give an overall explanation of why there is an Aristotelian option and how it's an alternative to Platonism and nominalism. People seem to have trouble in seeing why Platonism and nominalism don't exhaust the field. And those two articles explain that clearly. Then there's Anne Newstead's Indispensability Without Platonism. That's interesting because Platonists have come to rely heavily on the indispensability argument, which says that reference to mathematical entities is indispensable in science, and therefore you should believe in them. Well, that's correct, but you don't need to believe in them as classical Platonist abstract objects. Newstead explains the Aristotelian alternative and how it fulfills the indispensability criterion. The next two papers, Kessler and Forrest and Armstrong, give the Aristotelian view on natural numbers, which I've hardly mentioned so far. The basic idea is that the number 4, I'll say this slowly because it's a little hard to grasp at once. The idea is the number 4, say, is the relation between a heap and a unit-making universal that structures the heap, such as, for example, there's a heap of a mass of biomass on the branch and being a parrot. Okay, there's some parrot stuff on the branch, and the way parrots are, it has to be so many parrots. It's the relation between the heap of stuff and being the universal being a parrot. Now, if you want an Aristotelian view account of sets, well, there's one in D.M. Armstrong's Classes of States of Affairs. Now, on an Aristotelian view, sets and numbers are not especially central as mathematical topics. Aristotelians suggest starting with applied mathematics instead, instead of investing heavily in set theory and formal logic. But those things are part of the story, and those are the accounts given. Robert Thomas is the editor of Philosophica Mathematica, and his argument is, in this paper mentioned here, is that mathematics is a science of something, but not of quantity. He says, instead, it's the science of relations as such. And that connects modern mathematics like category theory. That connects with modern mathematics like category theory, which does emphasize relations over objects. Strangely, Philosophica Mathematica has not published a single paper on Aristotelian realism. Mark Lange's paper, very recent paper, What Could Mathematics Be for It to Function in Distinctively Mathematical Scientific Explanations, writes this. It says, Aristotelian realism allows mathematical facts to be explainers in distinctively mathematical explanations. In science, as mathematical facts are themselves about the physical world. So that gives it an advantage in the current debate about how mathematical explanations in science work. Finally, there's Thomas' strand of philosophy of mathematics. So Thomism is a variety of Aristotelianism, but has its special features. In the mid-20th century, that was about the only part of the field that was live. The history of Aristotelian philosophy of mathematics is very strange. It was almost the only version in the field in, say, the 17th century, and for centuries before that, when we were all Aristotelians, and all of a sudden it disappeared in the 18th century without being argued against, and thought to have been killed stone dead by Frege, and had very little profile in the 20th century. Hopefully we're back now. But the Thomists in the mid-20th century at least maintained the true faith. It's not easy to explain exactly how that differs from the rest of Aristotelian philosophy of mathematics, but it has some tendency to concentrate more on epistemology, and it also tends to restrict the objects of mathematics to quantity. But anyway, we're going to hear more about that in the subsequent two talks. A good introduction of the field is Armand Maurer's paper, Thomas and Thomas Aquinas on the Foundations of Mathematics. The very new book by Andrew Unan on the relation of mathematical realism to realism in physics probably should count as Thomas too. He can tell us later in his talk. There's also Eduardo Berno's recent large thesis, which has a well-developed Thomas view. Well, that's a quick survey of some of the things out there, just to try and convince you that there's a lot, and a lot of variety as well. And actually, I think it's a feature, whether it's either it's a feature or a bug of Aristotelian realism, that it can have a lot of different sub-schools, because they can disagree about what features of the world mathematics is about, and that could be productive. Well, of course, there are some standard objections to mathematical realism. For example, what about idealization? Doesn't mathematics, as Aristotle himself said, study perfect circles and not the shapes of wheels and coins? And what about higher infinities that aren't realized in the physical world? And there are also some replies to these. Going into them now isn't quite appropriate, where the aim is just to give a basic introduction. Of course, there's plenty of debate about those matters, if they're the kind of things that bug you. Well, if after all that you think it's worth investing 15 minutes of hard work in grasping Aristotelian philosophy of mathematics, why not start with the Wikipedia article? I've done my best to make it clear and introductory, and you don't need to know anything outside itself. Thank you. That is all for the moment. Stop share. Questions, etc.
Wow, thank you. James, that was great. Little overview for everyone to connect all the talks we're going to be given today. Yeah, so any questions, I suppose, about the general layout that he's given, or probably other general questions about the field, since Dr. Franklin's probably the best position to answer them. Yeah, Rupert.
Thanks very much, James. One of the things I was curious about is, I don't know if you're familiar with Jeffrey Hellman's modal structuralism in Mathematics Without Numbers.
Yes.
Basically talking about, mathematics as being about modal properties. Are you able to say a little bit about, is that something you think could be fitted into the Aristotelian tradition, or is there a tension? Yeah.
Well, there's tension. Actually, I did say that his modal structuralism is the closest existing view to the present Aristotelian realism. Where it differs is that, in my view, his necessities are not properly grounded in in reality, in possibly physical reality. So he says, for example, that the truths of number theory are about if anything was an omega sequence, that is a series 1, 2, like 1, 2, 3, 4, etc., then it would have properties, certain properties. But it should, but there are omega sequences, either actual numbers or physical ones, and there are certainly fragments of omega sequences, and the necessities are actually realized in those. So what I think is that I don't agree with the if-thenism, so to speak, because I think those those necessities, for example, in number theory, are not just modal, they're actually realized in physical reality. Well, such as we're clearest in the case of the Euler's bridges. It's a wholly finite thing. There's no if-then about it. It's the necessities are actually about the bridges and people. So we don't need to be in some other Platonist world or some modal logic world either.
Okay. Thanks.
Andre?
Yeah, thank you very much. I think one problematic or probably weak point of Aristotelianism in mathematics that it doesn't provide really account, as far as I can see, for, say, constructive aspects of mathematics. Actually, we can see when in Aristotle's mathematical examples that he doesn't manage to account, say, for Euclidean like geometrical proofs in this constructive part. And then to see this, you need to contrast this Aristotelian approach not to Platonism or nominalism, but rather some version of, say, Kantianism, or today to some cognitive science approaches to mathematics, right? So I just wonder, what is your take on that issue?
Yeah, my take is that the constructions, for example, Euclidean ones and proof as well, are matters of epistemology, which should be kept separate from matters of ontology, and that there's techniques of proving something, but nevertheless the subject matter that things are proved about are not themselves constructions, but they're geometrical properties, like being circular and so on. So you study those by drawing a circle, but nevertheless the point of that is that there are a whole lot of circles actually out there, both maybe there's perfect ones as parts of space and imperfect ones as well, and your epistemological techniques are supposed to grasp the truth, in the internals of necessities that are out there in that world.
Yeah, but I think it's objectionable because in Euclid, you have at least, I think most of so-called propositions, right? They are problems rather than theorems. And when you have a problem, it's like first proposition of Euclid and last, they are both problems. They're not about saying truths about anything, right? But they're bound to constructing certain mathematical objects. And I think a part of mathematics is about that even today. So, and that somehow intervenes somehow in very special way with this propositional aspect, right? When we essentially taking truth. That's exactly the point.
That's a Euclidean technique to get him to something like Pythagoras' theorem. Pythagoras' theorem isn't about constructed triangles. It's about all right-angled triangles, especially even in the ones in the Euclidean space we live in, as he believes.
Yeah, but first it helps to construct regular triangle. Last one is to construct five Platonic bodies, you see? And these things are kind of epistemically valuable by themselves, not because they solve certain theorems. Yes.
But yes, you can, but still you can build a dodecahedron and the things that you've done in your constructions are true of it. The angles of a dodecahedron or whatever they are. So I think construction is a technique. If you were, perhaps if we had less papyrus and were more godlike, we wouldn't really need the constructions because we could just see them. So we'd have enough parts of space out there.
Thank you.
All right, I'll exercise my chair's privilege to push a question of my own. So, the picture you've given, of, okay, you've got nominalism and realism, right? And then within realism, you've got the Platonist kind and the Aristotelian kind, and then you've given us a kind of a rich portrait of what goes under the Aristotelian rubric and how different the views are, both in terms of their historical etymology and in terms of the details of what they're interested in pushing, that kind of thing. But I guess I wonder if you haven't been maybe a little bit reductionist about the contrast, or simplistic about the contrast cases in the Platonist and nominalist realm. So particularly I'm thinking of the question of Hartree-Field's 1980 program, which I think we're going to hear about a little bit later this afternoon from Lorenzo. But I mean, that view is generally taken as nominalist. And, if you look up, the nominalism page on the Stanford Encyclopedia, it's one of the cited views. But unlike his later view, it's not fictionalist, right? So he has a semantic disagreement with Aristotelian, so that he thinks that the kind of things that are mentioned in mathematical sentences don't strictly exist. But nonetheless, he thinks that there's a correspondence between those things and things in the world. So between, symmetries or numbers and, stuff that's arranged in certain numerical patterns or in certain arranged in symmetries. And so a big part of that program is actually trying to show that you can, do physics on that basis, right? You can take important, theories from modern physics and, get enough trigonometry and calculus, out of the world with these correspondences to, well, what he calls nominalize those theories. And of course, I'm reminded of the Aristotelian idea of doing that with infinities, right? Of like, okay, we've got these infinities in mathematics, but what kind of situation can we develop in terms of potentialities or whatever from the world to make sense of those without appealing to kind of Platonic objects? So I guess I just wonder if maybe it's a little too hasty to have a kind of a binomial, or a diagram, right? Rather than having something with a little more nuance or a little bit more of a spectrum where you go from like, really Fregean Platonistic theories where they're out there in abstract space with no causal powers, et cetera, then to, maybe more historical Platonistic theories where, yes, they're in some kind of abstract space, they're prior to rather than dependent on physical things, but they still have some kind of causal interaction with physical things, then to a spectrum of Aristotelian views, then out the other side to nominalisms like Franklin 80, or I mean, to Hartree-Field's 1980, then maybe further to, Hartree-Field's fictionalism or other kind of views. Or maybe we need a two-dimensional idea with dependence on one axis and the semantic question on the other axis. I don't know, just to kind of push you about that general landscape question.
Well, I think we don't need to do that, but we do need to classify people correctly. In my view, Hartree-Field is not a nominalist. His book says it's science without numbers, and it's certainly science without Platonist numbers, but it isn't science without quantities. If you look at what he's got in there, he's got a realist understanding of quantities like temperature. So temperature is something that varies across a physical space. So it's hotter here and colder over there. And the way he speaks about that, there's a number of hyphenations in there that are a little bit obscure, but he means he requires to have a realist understanding of temperature, varying mass and so density and so on. And they on an Aristotelian view, Aristotelian realist view, that's what you should be doing. Those are real quantities that vary across a space. So density may vary the same way as temperature, or it may not. But these are quantities, in realist quantities in the Aristotelian sense. How much you should study them with Platonist functions from R3 to R or something is a matter for mathematicians to decide. But for philosophers, it's to tell him that he's not a nominalist. He's an Aristotelian realist about the matters he's talking about.
Just a little quick pushback, but doesn't that sort of ignore the semantic question entirely, which is much of the motivation of the debate?
Well, yes, okay. Aristotelians are not interested in semantics. And they don't think it's especially relevant to philosophy of mathematics. It might be it's to philosophy of language and perhaps philosophy of mathematical language, but we're in another part of the woods. We're looking at quantities and questions about how best to study them, or whether mathematics is ideally studied with proof as in post-Greek mathematics, or without it as in Chinese mathematics. Well, these are questions that are not really about philosophy of mathematics. They're about, methodology of some kind. Good questions, but other ones.
All right, yes, Eduardo.
Yeah, you're muted.
Sorry about that. It's more a comment than a question to tie in what Andrei's question with James' response. That I think was a perfect response about Aristotle and the generation or motion in the case of problems in Euclid as opposed to theorems. Aristotle does say that the consideration of mathematics is without motion, and yet in the physics he shows that if you remove a motion, you remove mathematics as well, because mathematicians need motion. And the example that he gives is precisely that geometers say that a moved point produces a line. So that would pretty much include that motion. And that's all I wanted to say.
Yes, yeah, fair enough. Plato says somewhere that it'd be laughable if people took mathematicians talk about extracting square roots and adding numbers as to mean that because those are operations that happen in time, roots and numbers are entities that exist only in time. You might say the same about the construction of the set theoretical hierarchy as well. You inevitably think of it as constructed mentally in time, but that cannot be right.
Yeah, if I can just follow up, effectively in Plato, we're not talking about Platonism in today's sense, right?
Yes, that's right.
Plato's philosophy of mathematics. Mathematics has this double nature, right? Because it's somehow between what he called ideas or forms and this becoming. So physics, roughly, right? And so exactly that somehow it combines, according to Plato, these two aspects. One which is, say, about propositional truths, put in modern terms, and the other about constructing, right? And then if you compare that with Aristotle's account, right, then this, this constructive part is kind of reduced. So it comes down to what exists and certain truths about existence, right? And that's exactly the body that
Yes, all right.
I pointed to.
Yes, all right. But okay. But the fact that chemists work on, let's say, work out what they know about atoms by pouring things into test tubes doesn't mean that atoms are about actions. We need to, I think we need to keep a very clear distinction between methods of studying mathematics and methods of proving things and the subject matter, which is, as Aristotle says, about things that don't come to be or pass away.
All right, anyone else want to sneak in? We have about 5 more minutes. Yes, Rupert.
Yes, thanks, James. Can I ask just one more question? I just had a really quick look at your Wikipedia article, and I noticed in the section dealing with the higher infinities, there was some talk about uninstantiated properties. And you mentioned there was at least one Aristotelian who was willing to countenance uninstantiated properties. I always had the idea, and you might be able to tell me a little bit more, I thought believing in uninstantiated properties was a little bit of a problem if you were an Aristotelian, but I could be wrong about that. Maybe you could just comment on that a bit.
No, you're quite right that within the Aristotelian school, and we don't necessarily want other people to know this, we are fighting about that very question. So perhaps our recent world leader, David Armstrong, said that under no circumstances should you count in any uninstantiated properties as real in any sense. Whereas I'm a little bit more relaxed. I wrote, and I would call my position semi-Platonist Aristotelian, which is a little bit more positive about uninstantiated universals. So let me leave, it's nothing to do with mathematics. So let me move to the question about an uninstantiated shade of blue, if there were one. So let's say in a more primitive state of the universe, there's not that many shades of blue around. There could be, but actually there aren't. There's only several of them. And let's consider an uninstantiated one. Now, what about the scientists get onto the science of color? Well, is the science of color about colors, or is it only about instantiated colors? Well, there's something surely wrong with that question. I mean, if you get that colors are, let's say, have some continuous spectrum, which may, and some of those in the spectrum may or may not be realized. Well, it's not that the uninstantiated one is missing from the theory of colors. It's just not the business of the theory of colors to know which ones are instantiated. That's for observation. But and it's kind of the same with the mathematics of numbers that may be too large that are actually instantiated. They could be, possibly, if you had enough dimensions, maybe you could instantiate them in wood. But it's not the business of a science to tell you what's instantiated. It's to study the universals as such.
So
well, that doesn't quite answer the question.
Sorry, yeah.
Okay.
Yeah. In your view, could being an Aristotelian realist, that could be reconciled with being a truth value realist about set theory, or
yes, that's
yes.
exactly what I mean. Yeah.
Yep.
Whereas not everyone is going to agree with that, but I would certainly agree with that.
Okay. All right. Thank you very much.
All right. Thank you, Dr. Franklin.
Thank you. Thank you.
All right, and next up we have Daniel Uzma Gomez, the University of Lorraine. Daniel, do you want to show your slides? Perfect. And can that be made full screen? Yeah.
Okay, do you hear me?
Yes.
So, and do you see me?
I see your slides, but not you.
Okay.
I don't think your camera's on.
So
There you go. And then can you make your slides full screen? Is that possible? Yes.
Okay.
There, you're perfect. All right, let's give just a minute in case anyone wants to come just for your talk to make sure we don't start without them.
Okay. So thank you to